Let's get started on a short discussion of the material in sections 2.1 and 2.2 and see how those work. You've dealt with things like what's addressed in these things before, but in a math class you tend to just see it as the distance equals rate times time equation. We're using that here, but for us, we're going to use somewhat fancier language. For a distance, actually this will be a displacement now, we're going to call this delta x, a change in position on the x-axis. And it'll just be x2 minus x1, where we went to, or how far we moved from time 1 to time 2. Instead of t, put an arrow on these things, we're going to talk about a time interval, which will be t2 minus t1. And we'll have some ordered pairs of information here. One ordered pair would be x2, t2, and the other one will be x1, t1. And these two are tied together. x2 is the position at time t2, x1 is the position at time t1. Now, for starters here, we'll talk about, instead of calling it R for just plain rate, we're going to call it, I tend to call it just V average, but your book does a little more with that. Looking ahead is actually what they're doing. They call it VAV-X, and by that they mean the average speed in the X direction. When we combine all this stuff together, if we solve for the rate, which is actually going to be V average in the X direction, up here if we solve for rate, we just get distance divided by time. But if I do all the substitutions that I've got here, time is going to become this, distance or displacement is going to become this, I'll get that the V average in the X direction is going to be x2 minus x1 divided by t2 minus t1. And it's just the distance traveled, the displacement, divided by how long it took to get there. And that's the average velocity in the x direction. For a sample calculation of how you might do something here, let's suppose that our initial position was, put a 1 on there, 5.0 meters. Our final position was 17.2 meters. Let's suppose T2 is equal to 3.5 seconds and T1 is equal to 0. That's when we started our stopwatch. So the average velocity under these circumstances would just be 17.2 meters minus 5.0 meters divided by 3.5 seconds minus 0. By the way, usually I would just not bother to write that minus 0 because it doesn't really do anything. And if you calculate this out, you'd have, what is it, 12.2 meters on top and 3.5 seconds on the bottom. Turns out this comes out to 3.5 meters per second, and we can keep two significant figures on here. So there's a sample calculation. We'll do another one here. Let's suppose that our initial position is x1 is equal to 2.2 meters, x2 is equal to 14.2 meters, and T2 is equal to 6.5 seconds, T1 equals 2.5 seconds. So in this case, wait a sec, I wanted to change something here. I'm going to make this x2 and this one x1. I wanted to illustrate a different point as well. This time, V average in the x direction will be x2 minus x1 over t2 minus t1, and this time 2.2 meters minus 14.2 meters divided by 6.5 seconds minus 2.5 seconds. This is going to be negative 12.0 meters on top and 4.0 seconds on the bottom, and that comes out to the average in the x direction is minus 3.0 meters per second. Okay. We get a negative sign on this one. Well, we started at 14.2 meters, we ended up at 2.2 meters. This thing is going in the negative x direction, that's why. In this case, in the one-dimensional motion, the sign on the V thing tells us the direction it's going. When we have information about how fast it's going and what direction, we call that velocity. That's why in physics we use a V to stand for the rate of something, but we'll call it velocity whenever we have that information. We'll deal more with that in some future lessons, but that's something I wanted to point out here. Now, the book also discusses making graphs of some of these things, and this is some place where what we're going to do in this class will differ from what you've always done in math classes. They talk about making an x versus t graph, and you may have a position here. This might be where the object is at t1. At that time, we'll call that point x1. And then at some later time, t2, the object might be up there, x2. Well, let's see. That x2 minus x1, that's just this thing. Delta x, x2 minus x1. The t2 minus t1 is this little span here. That's what we call delta t. Okay. And the V average in the x direction ends up just being delta x over delta t. That may be a little bit familiar from your math classes. That delta x over delta t is the slope of a line that connects these 2 points. Okay. That's what delta x over delta t is. But we don't actually know in this case that that's the path that the particle took on an xt graph. The particle could have done anything. It could have wiggled around like this, gone off to Timbuktu, and then come back to that point. But if all we have is x2 and x1 and t2 and t1, that's the best we can do between those 2 points. That's why we call it an average. The particle could have gone absolutely nuts like this in between there. But all we can get from those data points is an average velocity. It might be more interesting to be able to calculate an instantaneous velocity. That's not going to be so easy with some of these things, but that's the next section in the book, is talking about an instantaneous velocity. So let's consider an instantaneous velocity here. I'll try to make a nicer graph this time, and a bigger one. Okay, there's my x-axis. Is it troubling you to have an x-axis that goes vertically? Here's my t-axis. So t in this direction, x in this direction. And I can start off with an, let's see, call this point here t1, x1. That may be a little troublesome, but That's the way we've got the axes going. We usually put the coordinate on the horizontal axis first and then the one on the vertical axis second. We're not going to be doing a lot of things like this, so don't worry too much about that. And this will be x2, t2. Notice that I managed to get the order wrong on that second ordered pair there. It shouldn't matter with what we're going to be discussing next. Now, if I was to calculate a velocity based on those 2 points, what I would be getting is the slope of the line that connects those 2 points. But let's suppose that the actual x versus t curve looks like this between these 2 points. Okay, and suppose that I want to know how fast is the thing going right here at this instant. This particular slope may not give me that. So what can I do about that? Well, I can start sneaking up on here. I can calculate the slope between these 2 points instead. That may not give me the value yet. I can calculate the slope between these 2 points. And if I do that, I'm probably going to get pretty close to that value unless this thing had a lot more curvature. What I'm doing is shrinking down the time interval. That ends up shrinking my x interval as well. But by shrinking the time interval, I'm sneaking up on the slope of the curve at that point. This is something you're going to be doing in calculus very shortly, but it's a limit. I'm going to look at the limit as delta t goes to 0 of delta x over delta t. We sneak up on the thing that way, and you're going to learn to do this in calculus this quarter. It's called taking a derivative, and we would call that just plain v sub x, and we'll call it the instantaneous velocity.